So for the thing slash warm up, I have what do you notice about the vectors and their the geometric I should have said geometric vectors and their algebraic representations. V equals 5, 4, and U equals -1, -5. And anyone besides Colton is allowed to answer this question. Sorry, Colton. Colton, we just went over this yesterday when you asked me in an email, but it was my warm up for today. Do we notice about anything about what's the relationship between these two geometric vectors and their algebraic representations? Is there a way we can tell which one's V and U? You guys might be overthinking it. Yeah, right? So the one that's 5, 4 is 5 in the x direction and 4 in the y direction. That is exactly it. Awesome. Right. So it's kind of like an ordered pair, like kind of like x, y. Except now we just have I just use less than and greater than signs because on equation editor is an absolute pain to put in vector things all the time, but they're supposed to be more up and down like that. Just so you guys know. They're not supposed to be like less than and greater than signs. They're supposed to be kind of more vertical. But yeah, so vectors can be represented algebraically by ordered pairs. For example, the ordered pair 5, 4 can represent a vector who's in center position and its terminal point is 5, 4. And so it's nice to think of the vector 5, 4 as the resultant of a horizontal. And when I say the resultant, I mean, so we're going to go horizontal, a horizontal vector of 5, and then a vertical vector of 4. And so the resulting one would be 5, 4. Right. And since vectors with the same magnitude and direction are considered equal, the initial point of a vector can be any point in the plane. And so basically what I'm saying is 5, 4 doesn't have to be in standard position, but it can be anywhere on that graph, right? So if I go back here and I do a 5, 4 like this, it's obviously probably not exactly 5, 4, but that's still a vector of 5, 4, right? Whether it's in standard position or not. So we can use the distance formula or the Pythagorean theorem to calculate the magnitude of a vector algebraically. Okay, so I'm doing this in a very general way. From point 1 to point 2, we can see this, and I want us to find this. So what is the length of this segment here? Anybody? Maybe if I had, let's say, what if this point was, I don't know, -3, 2, and this point was 8, I don't know, 10. Yes. And so, okay, that line would be 11, right? Because the distance from -3 to 8. What's a way to do it if I just have generic x2 and x1? Brilliant. Absolutely. Right? this is going to be x2 minus x1, your second point minus your first point, right? 8 minus -3 is going to be 11, right? That's your distance between these two. And so this one is going to be y2 minus y1. Same idea, right? Now, to find the magnitude or the distance, right, we just use the Pythagorean theorem on these two, and we get that the distance or that the magnitude is the square root of a squared. A is going to be x2 minus x1 plus b squared y2 minus y1. And then take the square root of both sides to find the distance. You could write this down in your notes, but you guys know this, right? So I don't really like the memorization of the distance formula as much as I do just think about it as an x and a y, right? What's your distance this way? What's your distance this way? And then do the Pythagorean theorem because you have a right triangle. Right. So write an ordered pair that represents the vector from -3, 5 to y4, -2. Then find the magnitude of xy. So maybe for an example like this, I'm just going to sketch a graph. I'm not even going to sketch it like accurately with tick marks. I'm just going to do a general. So x being -3, 5 up here maybe. So -3, 5. And y is +4. 1, 2, maybe that's 4, and then -2 down here. And so when we say x, y like this, what we're saying is we're going from x 4. We're going from x to y, right? And again, I don't want, I think instead of, doing this formula, you can if you want. I think it's much easier just to think, okay, well, let me make a right triangle. The change in x, right? Or you can even just put this distance formula as the square root of the change in x squared plus the change in y squared. Might be an easier way to think about it. All right, but I'm thinking just do the Pythagorean theorem. So from -3 to 4, we go 7, right? This is the distance of 7. And from -2 to 5, we also go 7. And so then our magnitude is going to be the square root of 7 squared plus 7 squared, or 49 plus 49. Which, if I round to the nearest tenth, is going to get me 9.9. Go back. Do you want me to go back to this slide? Here. Good now? All right. Oh, we found the magnitude kind of early, right? What it also wanted is it wanted to find the ordered pair that represents this. So the ordered pair that represent this vector is -7, 7, right? Because we're going down 7 and then to the right 7. Or wait. I'm so backwards. I'm a math major. I know my x's and my y's. We're going 7 to the right and then -7. I was thinking -7 first because it went down first, but you could also go to the right and then down. Right? Y value is going down 7, x value to the right 7. So that's our ordered pair, and then that is our magnitude. Operations with vectors. I wouldn't really worry about writing all of this down because I think it's pretty self-explanatory. If you add vectors, for example, A and B, you would just add like pretty much accordingly, right? So if you add A and B, you're going to do A1 plus B1, right? Add those two and put them there, and then you would add A2 and B2. So basically add both the x's together and add both of the y's together. Same thing for subtracting. You would subtract the x's and then subtract the y's. And then if we have a scalar multiplication, scalar just means like a single number outside, right? Not another vector. You just multiply both of the components of the vector by that scalar multiplication. I wouldn't worry about jotting all that down because I think it's pretty intuitive and self-explanatory. If you want to jot it down, I would just leave some space in your notes so you can go back later on the video and just write them down. And so for example 2, we have let m, n, and p equal all these vectors, find each of the following. So m plus p, well, we know m is 5, 7, plus p is -1, 3. So we added vectors geometrically, but now we're just going to do it algebraically. It's very easy. We just do 5 plus -1, which is 4, and then 7 plus 3, which is 10. Right, and then m minus n, again, m is 5, 7. N is 0, 4. 5 minus 0 is 5. 7 minus 4 is 3. All right, not too bad. 2m, so that's going to be 2 times 5, 7. Plus 3n is going to be 3 times 0, 4. Then minus p, p is -1, 3. Then when we do this, this vector is going to become 2 times 5 is 10, times 7 is 14. 3 times 0 is 0. 3 times 4 is 12. And then minus -1. And then we'll end up with 10 plus 0 minus -1 is going to be 11. 14 plus 12 is going to be 26, minus 3 is going to be 23. I know I went a little speedy for that. Does anyone need me to scroll back up? Or does anyone have a question? It's basically just add, subtract, multiply, right? If you can do that, it's just about keeping track of basically your x component and your y component. I'll leave it there for a little bit if anyone's finishing up. What more slides do I have? Well, we might be able to get through this. Okay. And then the last thing to shove in your brain, a vector that has a magnitude of 1 is called a unit vector. A unit vector in the x direction is represented by I. That's supposed to be an I. And a vector in the y direction is represented by a j. So I is 1 in the x direction and j is 1 in the y direction, right? So I is just going to the right one, j is going to the up one, right? And so It might seem like weird, like why do we kind of need this? It'll become useful later, right? Because sometimes it's nice to deal with variables instead of like doing vector stuff here. So any vector a1, a2 can simply be expressed as you have you have a1 units to the right and a2 units up or down. Also, I know I have little arrows on all these vectors, but much more common notation is just doing this thing, which is also a pain to do in equation editor, so I don't bother. Abby, did you just mean scroll up for the slide we're already on? Okay. Okay. So our last example, write AB as the sum of unit vectors for A 4, -1, B 6, 2. Again, this isn't really necessary. I just like to draw pictures so that in the end I can kind of compare, see if I've done the right thing. So 4, -1 is, maybe here. And 6 is going to be past 4. And up 2 is going to be here. So A was first, then to B means we're going to B. And so our change in X and our change in Y, our change in X, we're going from -1 to 2. Or sorry, I don't know why I've mixed this up twice now. We're going from 4 to 6. Right. So our change in X is 2. And then we're going from -1 to 2, which is 3 for the Y. And so how we'd write this in a sum of unit vectors is we would write 2I plus 3